So everything we discussed in the past couple of classes, the Markov random process, Markov processes, Markov decision process, was everything clear, or did you guys have any questions? Some stuff that just went clear over your head and you're here in the classroom for form's sake. Anyone with questions, doubts, something that didn't make sense? Because we're going to be building on a couple of equations that we talked about in the last class. So let's start here. Everybody remember how, are we on? Yep. So does everybody remember how the state transition probability matrix was actually a function of the action taken, right? So in this little fly example, if you move towards the fly jumped, the state transition probabilities, you got one set of transition probabilities. If you moved away from the fly, it didn't move, you had a completely different set of transition probabilities. In this particular case, moving away had a very deterministic effect of increasing the distance. Moving towards the fly gave you two possible states, right? You either decreased the distance further or increased it, or maybe nothing happened. So we are familiar from the earlier discussion with the notion of the value assigned to any particular state. Again, I'm speaking of the information state of the system, not the physical state, right? So we are familiar with the notion of the value assigned to any state. And the value assigned to any state is the immediate reward at that state plus the expected value of the discounted expected value of the states that you could arrive at once you made your move. And because the transition probability was dependent on the action, the value actually depended on the action, right? And so if you change the action, if you had a specific action that you always took at any state, then depending on the action that you chose, the value function actually changed. And what was this business of having a prior plan of the kind of action that you would take in any state called? It was called a policy for the state, right? And you could also have a stochastic policy where you might say, sometimes I'm going to move towards the fly, sometimes I'm going to move away from the fly. In which case, you actually had two possible value functions to choose from. 1/3 of the time over here, you got this value function. 2/3, you got the other value function. So the overall value function for the state was the expected value of the state over all possible actions, where, for each action you had a corresponding action-dependent reward for the state and an discounted action-dependent expectation of the values of the state at the next instant, right? So this we remember. And based on all of these, we also said that we noted that these values were action dependent. So when I assigned an overall value to the state, I was averaging over all possible action dependent values. So I could actually define two kinds of values. One was the value assigned to the state, which was a function of the policy, right? And an action value pair, which was or an action value function, which was the value that we would assign to the state if you only chose a specific action. In this case, this is the value that you would assign to the state if you decrease the distance to the fly. This is the value that you would assign if you increase the distance to the fly. So the Q's are action value functions. The V was the overall value function. And observe here that the Q really is the current reward, action-dependent reward, plus the discounted expected reward over future states, expected value over future states. This is not action value. This is the overall value for the state. This made sense, correct? The whole thing. And so we could define an action value function, which is the immediate reward based on the action, plus the discounted expected reward over future states, also based on the action. The transition probabilities were based on the action. So we could combine the whole lot. We could define a little iterative formula where the value for any state was defined as the expectation over all actions for the given policy of the discounted expected value of the states of the future state. And so also you could define the action value function as this is no longer an expectation here. This is just the immediate reward that you get in response to the action at that state. And now you're getting an expectation over a discounted expectation over the values of future states, where the transition probability again is action dependent. So all of this was kind of, we spent a lot of time on this. Now these are going to be very key, very key formulae. Everything else that we're going to talk about, these have to make sense. Do they make complete sense to everybody, right? You should be able to write them out and derive them on your own because it's really not very complex. It's 2 terms. It's fairly trivial. And these are going to be the basis of everything else that we're going to be talking of in this class and the next class when I come back, and if I manage to squeeze another class out of you guys, the final class, right? So here are the 2 functions. Here are the 2 formulae again. This is the formula that tells you how to compute the value for any state, right? By the way, for those of you who are not in class, you better be watching the video because this is all going to be in the quiz. And these slides are not going up until next week. Now, so also for the action value, you have the formula. We have the self-referential formula where you can define one action value function in terms of other action value functions. So when I speak of solving a Markov decision process, I shouldn't be using the term solving. I should really be speaking of computing the Markov decision, the value of a Markov decision process. What I'm saying is that I give you a complete definition of the process. What are the states of the process? What are the action-dependent transition probabilities for the process? What are the rewards, or what is the probability distribution of rewards at each state in response to each action? So these probability distributions now actually become action-dependent. What is the discounting factor? I give you all of this. I give you a complete description of the Markov decision process, and then now I ask you, what is the value of each state? And this can be found using the Bellman expectation equations, which basically are simultaneous equations which relate the value of each state to the values of the other states, right? I can write the entire thing up in matrix form as we saw earlier. Remember, when I was writing things in matrix, even when we were speaking of Markov reward processes, I showed you how you could write all the values of all the states. As a vector, you have the transition probability matrix. So in matrix form, the value for any state, the value vector, which is the values of all the states, is going to be the sum of the reward vector, which is the rewards for all the states, expected rewards for all the states under a policy. Now what is this R pi? This is the average over all policies, the R pi, plus the discount factor times the transition probability matrix times the reward in future states, right? So the value of future states. Once I write it in this manner, now it's easy enough for me to solve for the value functions for all the states. Now, by the way, there is a little bug, Ryan, you should remind me. There's a little bug in my slides. I should really be this. I think the transition probability matrix is supposed to be transposed. I've written the formula wrong, but I'll check it out. Anyway, what is the problem with this? Trying to solve for the value function in this very naive manner. If I only have 8 states, this transition probability matrix is going to be 8 cross 8. It's easy enough to invert. If I have 8,000 states, the matrix is going to be 8,000 cross 8,000. It's going to be much more difficult to invert. If I have 8 million states, it's going to be impossible to invert. If I'm playing a chess game with 10 raised to 120 states, there's no chance you're ever going to be able to do this, right? So while there is a solution, it's not clear that you can actually compute the solution. Now, let's go back and let's move on. We spoke of a policy, which was how we decided what action to take at each state, right? So we saw 2 examples. I don't know if I have the for some reason this machine has not synced the file. It hasn't. So I've moved slides around and then okay. So let's go back over here because the slides on the Surface have not updated. Now here there were 2 different policies, right? Here was a policy where Here was a simple policy where it said at every state I'm always going to try to get closer to the fly. Here was a different policy where it said that if I'm a distance of 1 from the fly, I'm actually going to try to move away from the fly. At other times, I'm going to try to get closer to the fly, right? Which of these two policies was better? The second, because the first policy pretty much guaranteed you that you would never catch the fly. As soon as you got to position 1, if you followed this policy, you're always going to stay at a distance of 1, the spider is going to die. Whereas here, if the spider is smart enough to move away from the fly, if it's only a distance of 1 away, then at the next move, it's going to be at S2. And at S2, if it moves closer to the fly, there's a 1/3 probability that it's going to catch the fly, right? So clearly, there's an optimal policy. What was the optimal policy over here? The optimal policy was that if you were at S3, there was only one action you could take, no big deal. If you were at S2, moving away is a very stupid thing to be doing. So the optimal policy was to try to reduce the distance to the fly. If you were at S1, the optimal policy was to actually move away from the fly, right? So there is a notion of an optimal policy. Now this is a very simple example. Clearly, if I make the system much larger, how do we decide what the optimal policies are? Because at each state, there are many possible actions you can take. What action should you take to actually maximize your returns, your profits from the system? And again, what do we mean by that? What action must you? So we really want to be choosing a policy such that this term, the value of the value associated with every state, which is the expected total return if you began at that state, to be maximized. This is what you want to be maximize. This is the action. This is the policy you want to take, right? And again, why do we consider the discounted return? Because if you didn't discount it, if you didn't have gamma raised to k, this is 1, and if you had a finite reward from every state, this is going to become infinite. So there's the arithmetic kind of collapses. None of this makes sense. You need to discount things for stuff to work, okay? So now, so here it is. If I begin speaking of a policy, right? If I'm speaking of an optimal policy, before I speak of an optimal policy, I need to be able to speak of a better policy, right? I need to be able to say policy A is better than policy B. If I don't have some way of ordering things, there's no notion of saying what is the best thing, right? So you need to be able to define an ordering of policies. And we say that a policy pi is better than a policy pi prime if the value function under pi is greater than the value function under pi prime at every state, right? So this is a very greater than or equal to the value function at pi prime at every state. So this doesn't mean, for example, if I have one policy which has values, 10, 10, 10, 5, 10, 10, 10, and the other one was 0, 0, 0, 10, 0, 0, 0, I can't make an ordering statement. This is not a strictly ordered, policies are not a strictly ordered set, right? The only time you can actually compare the two is that if at every state, if I have two policies, at every state, one policy has a value that is greater than or equal to the value for the other policy, then I say the first policy is better than the other policy, second policy. Right? So this is a notion of ordering of policies. Under the better policy, you will expect better overall outcome no matter where you currently are, right? Which makes sense. Whereas if you had two policies where the ordering, where the relative values of the values for different states kept flipping between the two policies, there are some states where you could begin, you'd be better off beginning with one policy. There are other states where you'd be better off with the other policy, right? That doesn't make sense. So there's no notion of ordering over here. Whereas if you define things in this manner, you will expect the better overall outcome no matter where you begin, right? So there's a theorem that's actually quite easy to prove, but I'm not going to try to do this, which is that for any Markov decision process, there exists an optimal policy. What do I mean by there exists an optimal policy? There is a policy pi star such that it is better than or equal to every other policy that you can think of, right? And specifically, if there are multiple optimal policies, then the guarantee is that the value functions for all of these multiple optimal policies are going to be the same at every state. So you can actually have different policies with the same value function, right? You could have a policy which says, one policy which says I'm always going to go right. The other policy which says I'm always going to go left. You could have policies which are mirror images of one another in some settings. But then once you actually compute the values for every state, they would be identical under both policies if the two policies are both optimal, right, at every state. In any case, this holds. If you have a Markov decision process, there is an optimal policy. Okay. If you take that for granted, then that holds not just for the value function, it also holds for the action value function, right? This business of optimal policies. So now, suppose I told you this, and I ask you, what is the optimal policy at any given state? You're allowed to compute these guys, the value function corresponding to every single action, right? Then if I gave you this and I asked you, what is the optimal policy at any state? Which action would you choose? What would the policy be? Anyone? So this guy tells you what the value of the state is if you took an action A. Let's say there are 5 possible actions, right? And you say, if I take this action, the value is 5. If I take this action, this value is 6. If I take this value, the action value is 7. This is 8 and this is 9. What is your policy going to be? You're always going to take the action which gives you the largest action value, right? So in other words, the optimal, the relationship between the two is very trivial, in that the optimal policy for any state is to choose the action that has the largest action value function under the optimal policy, right? Very easy, and it makes sense, intuitively kind of makes sense, which basically says, that the value, optimal value for any state is simply the largest of the action values. These two are basically making the same statement, right? So the action you would choose is the one that results in the highest action value. And if you're always going to be choosing this action, then the value really is going to be, overall value is simply going to be the largest action value, right? Simple. Now, questions? Anyone? I know everybody's sleeping, but this has got to be straightforward. So there's something called a backup diagram. I've stolen this from Sutton, cut and paste, PDF. Everybody who teaches reinforcement learning eventually uses Sutton's book. And if you use Sutton's book, you're going to see these figures. I don't hold much with these backup diagrams myself. I would represent things differently. But this is something you're going to see. So here's how they define it. So let's say you're at a state S. From a state S, you can take multiple actions. Each action is going to end up is going to give you a different action value, right? So if you took action A1, you're going to get this action value. If you took action A2, you're going to end up with this action value. If you took action A3, you're going to end up with this action value. And so which is the one that you would actually choose? You're going to choose the largest of the three. So you're going to choose the max, right? So this, he calls this the backup diagram. The blank states are circles. These are all the possibilities. He's listing all the possibilities and the corresponding values. And the optimal policy becomes obvious when you actually see the figure, right? So now, skip this. What is the optimal action value for this guy? The optimal action value for any given action is the reward that you're going to get for this action from that state, plus the average over all future states of the values of those states, right? So when I go from a dot to these circles, I'm really taking an average over these two guys to compute Q over here. So you see how the diagram is actually represented. From a state, I'm going to 3 dots, which shows you the 3 possibilities for actions. Dots represent choices over actions. Circles represent choices over states. And so here I have three possible actions in this figure, which would lead me to these three possible situations in the game. And each of them has a different transition probability, right? Because you have action-dependent transition probabilities. So based on that, you have different possible futures over states. And if you want to compute this action value function, you're going to be computing the reward there plus the average of the values of these guys, discounted average of the, right? So you could compute it for each of these. Optimal, the value for the state under the optimal policy is going to be the max over all actions of this guy here, which is simply the action value for under each of those actions, which is averaging over all the states that you can possibly get to. Right? This is just a simple pictorial illustration of how the whole thing works. Now, anyway. Something happened. Nope. So I'm back to poking Ryan. Oh, perfect, right? So, but then go back and let's do the same thing again. What is the optimal action value for any state? The optimal action value for any state is going to be the immediate reward plus the discounted expectation of the optimal values of all downstream states. Because if you're working on an optimal policy, everything is optimal, right? So Q star is going to be dependent on V star, right? And V star in turn is going to be the maximum over all action values downstream, right? So basically that's what we are saying, that the optimal action value at any state is the reward at that state plus the expectation over the values, discounted expectation over the optimal values for all states you can get to, where this value again is simply the largest maximum over all possible action values in the next state. And if you combine all of those two, you get this interesting situation where you also see that the action value for optimal action value for any state is the immediate reward plus the discounted expectation of the maximum action value over all possible states at the next instant. So you're getting a max in the function as well. This just sort of shows you how the whole thing works, right? Anyway, moving on. So these are the two equations that we actually sort of got from the diagrams. They're going to be on the slides. But now here are the optimality relations. If I gave you the optimal action values for every state action pair in the Markov decision process, it's trivial for you to compute the optimal values for every state by just picking the largest of the action values at each state. If I only gave you the optimal values for the state, not the action values, it's trivial for you to compute the optimal action values for each state using this little recursion, right? And if I gave you either of these guys, it's trivial for you to compute for you to compute the policy, right? So all of these three terms, well, the first two are kind of interchangeable. In terms of computing the optimal policy, if I gave you any of these three variables, you should be fine, right? So now when I speak of solving a Markov decision process, what I'm really speaking of is finding the optimal policy, pi star, for the process, which is equivalent to finding the optimal values for each state, which is equivalent to finding the optimal action values, because all three are equivalent, as we saw. So now when I ask you to solve a Markov decision process, all I'm saying is find one of these three guys. Because what am I really interested in? At each state in the game, at each state in the system, I am interested in finding out what my best future action is. And to find my best future action, I need to solve this, so solve the entire, solve these equations. And you have various solutions. You have, which are going to estimate one or the other. Value-based solutions are going to either estimate the value functions for each state or the action value for each state. Policy-based solutions will directly estimate the policy. These are the two classes of solutions that we actually see. Okay. So there are no clause form solutions. The way you would do it is iterative solution, where given a Markov decision process, you're going to you have planning and control, So given the Markov decision process, you're actually going to find the values of all the states. Given the values of all the states, you're going to find the optimal policy. Given the policy, you can find the optimal value and so on. And if you're not given the Markov decision process, then many of the things are actually unknown. And that's when, I've been talking about MDPs. I said this was all about reinforcement learning. Guess what? I just spent 3 lectures not even mentioning reinforcement learning. What I was actually talking about was Markov decision processes. If I'm not given an MDP, and now I have to learn the optimal policy from each state, then I'm going to have to guess something about the underlying process, and then guess the policy. And that's where you get these things called Q-learning and SARSA, and that comes under reinforcement learning. Okay? So, questions? This was the easy bit because, oh no, my figure is gone. But you haven't quite hit the steep curve of not understanding anything. Remember the figure I had in the beginning? So now this is just the knee of the curve, and now it goes vertically down. Okay. Yes. Right. If you have no questions, I'll just move on. Anything on the stream? No. Okay. So here it is. First, planning with a Markov decision MDP. You're given an MDP. You have to find the optimal policy, right? Or you can do one of two things. You can do a value-based solution where you try to find the optimal value function and derive the policy from it, or you can have a policy-based solution where you find the optimal policy directly. So this business of planning, solving an MDP, this business is to find the optimal policy given everything about the process. Okay. So let's look at the value-based function. The value-based solution is going to have 2 steps. It's going to have prediction and control. I mentioned control erroneously a couple of slides ago. So the actual business of solving or planning with an MDP has 2 steps: prediction and control. So in the prediction, given a policy and everything about the MDP, you must compute the value for all the states. In control, you have to find the optimal policy. They're 2 different things, right? If I give you the policy, what is the value for all the states? That's one. And now find me the optimal policy. That's a completely different thing. And we're going to come. So let's first look at prediction. It turns out you have to solve the first guy before solving the second one. And for prediction, basically, first question, how do you actually represent the value function for any state? I can just use a table, right? So here is the state, here is the value. I can just literally write a table, if you're writing code for it, which computes the value for every, which stores the value for every state. Or I can have a table which looks at action value pairs as my keys and stores the value. And in this case, it's going to store the action value function. Now, this kind of works when you have a discrete number of states or a small number of states. If you have 10 raised to 120 possible states, clearly you're not going to be storing these tables. So then you actually have to learn to approximate these things. And that's where things get even more interesting, right? But let's continue to play with the toy examples. Now, here is the Bellman expectation equation for the value function, right? We already saw this. The way I can do this is I can write the vector of values for every state as the sum of the expected reward at every state, which is basically the expectation over all actions of the action-specific reward, right? Plus the discount factor times the expected transition probability matrix for each state, which is simply the expectation over all actions of the transition probability matrix, times the value function vector. This is just a very simple, straightforward equation. This is exactly what we've written so far. I have written it in vector format, right? And when I write it like so, I can write the simple vector equation, V equals R times gamma times P times V, right? Which means I can solve it using this simple matrix inversion equation, the formula, which is trivial if the number of states is small, but not so much if it's not, right? Now, if I want to do action value functions, all that happened is that instead of taking expectations over actions, I just expanded the whole thing out, And this one actually ended up retaining the reward vector now retains rewards corresponding to all actions. This transition probability matrix became even larger. The action value vector became even larger. If I want to solve for this, this is going to require, inverting an n times m matrix, which is, if n is large, it's impossible. If n times m is large, it's impossibler, if such a word exists, right? So how are we going to solve this? And so after having spoken all kinds of profound arithmetic for 3 lectures, I want to go back and revisit kindergarten, right? Almost kindergarten. It's great fun. I'm going to give you a little solution problem. Ax equals b. How many of you know how to solve this? Okay, this is not kindergarten, basic algebra, right? I give you a, I give you b, I want you to compute x. How would you do it? X equals b divided by a. Very trivial, right? I'm giving you some extra bit of information. A lies between 0 and 2. Okay? And I'm telling you, you are not allowed to divide. You've been through school, but somehow you never learned division. All you learned was multiplication. Okay? Solve this equation. How would you do it? You want to try what x is one at a time? That's a good answer. Anybody who can give me a smarter answer than that? It's not an unsmart answer, but it's a very inefficient answer, right?
Oh, you can see that because it's mono-inclusive, so you can know what's the sign of it.
You're getting closer. Anybody? How can you actually solve for this? Ax equals b. I'm giving you a. I'm giving you b. I'm just not letting you divide. How would you solve this? A to the negative 1 is a division. Right? Okay. So let me solve this for you, right? I'm going to write this as, so I'm going to first move ax to the right. So it's going to, if I rewrite this, I can write 0 equals minus ax plus b. I can add x on both sides. X equals 1 minus ax plus b. I've not done anything fancy, right? And now here is the crazy thing. I can use this little recursion. Start at any x. It's going to give me the correct answer. Why would that be? Remember the constraint I posed that a lies between 0 and 2, right? So let me start off at any x0. What is x1? According to this recursion. Right? What is x1 going to be if I start off with some x0? x1 is going to be 1 minus a x0 plus b, right? What is x2? So tell me. 1 minus a squared times x0 plus 1 minus a b plus b, right? What is x3? Is going to be 1 minus a cube plus 1 minus a square, and what is this going to be? X. What is x3 actually going to be over here? This is 1 minus a times x, right? 1 minus a b. 1 minus a b plus 1 minus AB plus B. See a pattern? So this is eventually going to be, so I can write xn equals 1 minus a raised to n plus 1 minus a raised to n minus 1 b plus 1 minus a raised to n minus 2b dot dot b, right, which is going to be 1 minus a raised to n plus summation I equals what? 1 to infinity, is it? 1 minus a raised to I b. This goes to 0, of course, if a is less than 2. 1 minus a has a magnitude less than 1. That goes to 0. And what is the sum of the geometric series? 1 over 1 minus a. Right? This goes to 0. So this is going to be b over 1 minus a. Beautiful, right? So nobody taught you that in school, but they should have. So what does this tell me? Why did I go back to basic algebra and series? Yeah, that's my proof. Right? Look at this guy, right? I had ax plus b is, someone wants me to bury their uncle. Never fails. Okay. So x equals ax plus b. This is exactly the same equation that we have over here, right? And this, so long as the eigenvalues of a are less than 1 or less than or equal to 1, I should be able to solve for this using the same recursion. Correct? That's basically the same problem all over again. A, in this case, for our Markov decision process, was a transition probability matrix where the diagonals kind of cancel out, right? So for a transition probability matrix, you're guaranteed A, that every transition probability matrix has an eigenvalue of 1, and all eigenvalues of the transition probability matrix of a Markov process are going to be less than or equal to 1. Anybody remember that? Right? It's very straightforward, right? If I were thinking of a transition probability matrix, the rows sum to 1, right? So that really should have been a transpose, but it doesn't change the argument. So if I have think about this. I have P11, P12, P1n, P21, P22, P2n, and so on. If I multiply this by a series of 1s, what do I get? This is going to be summation I, P1i, summation I, P2i, summation I, Pni, right? Which is going to be 1, 1, 1, 1, 1. In other words, this is an eigenvector with eigenvalue 1. Trivial, right? You can actually just work this, expand this arithmetic out a little bit, and you can show quite trivially that every single eigenvalue is upper bounded by 1. So the magnitude of every eigenvalue is upper bounded by 1, which really tells us that this guy satisfies the property that we gave you in the scalar case. In other words, I can just use this little recursion to solve the problem. But now that form, that x equals ax plus b, looks very familiar, doesn't it? It looks like this guy, where we said P is a transition probability matrix and has the eigenvalues less than or equal to 1. In other words, I can solve it like so. Right? Very easy. I mean, you can actually prove this in vector form. I just took the scalar version of it because it's kind of easy and fun, and would seem so obvious, but isn't. Anyway, so, and this will, so long as the eigenvalues of P satisfy our criterion, which they do, this is guaranteed to converge to the correct answer, except how many steps is it going to require? Infinite, but I don't really need to wait for it to converge. I can just say, so long as the value functions don't change, the largest change in value function is, lesser than some epsilon, I can stop because it's not going to change much beyond that. So this works very trivially if I gave you a Markov decision process, very large, and I asked you to estimate the values for all the states, very easy. You just sort of literally implement this code. And it doesn't matter how many states there are, even if you have 1,000,000 states, each of those is just like a single loop, right? And so you can iterate over this. It's going to be way cheaper than inverting matrices by many orders of magnitude. And you can actually do this in batch mode, meaning you just update all the states, or as you visit the states, you can keep updating. It doesn't matter which way you do it. This is guaranteed to converge. So what is the first thing we've just said? This classic dynamic programming. That's basically what we're doing, right? So anyway, so what have we just done? Given a Markov decision process, which was too large for you to just invert matrix. Firstly, given a Markov decision process, I told you how you could write out the values for all the states as simultaneous equations for any given policy. Why any given policy? Because the transition probability matrix was policy dependent, right? And I also showed you that even if the number of states is so large that you cannot actually invert matrices, there's a very simple algorithm to compute the values of the functions, from the values of the states, right? So here's a little example from Sutton, and let's work this out. Especially those of you who are asleep or watching out the window, I'm going to ask you. Okay, so here is this. Yes, yeah. Anyway, if I startle you, it means I just woke you up, right? So here's a little example, right? This is a little grid world. Everybody lives in this 4x4 square, and there is these guys, the two dark squares are home. If you get there, there are no more expenses. If you're in any other box, then you have to make at least one more step, right? So every box has a reward of -1 because you're going to have to take one more step, okay? There are 4 possible actions. You can move up, down, left, or right, right? And if you take an action, and our policy is random, which means that if you're in any box, then the probability of choosing one of these actions is 1/4, okay? So now, look at this box 12, right? So can you give me the transition probability? So here it is. If you hit a wall, you're going to bounce back and come back in the same box. I want you to give me the action-dependent transition probability matrix for this guy, the policy-dependent transition probability matrix for this guy. Transition probabilities from state 12. So what is P13 given 12? Thirteen is half? Yeah, yeah. 1/4. And what is P8 given 12? Is going to be 1/4, and P12 given 12 is half, right? Same thing for 13, what would it be? Okay, so what would the, yeah, so 1/4, 1/4. So 1/4, 1/4, 1/4, and 1/4 was staying in itself, okay? And what about for 9? What are the transition probabilities going to be under this policy? 1/4, 1/4, 1/4, 1/4, and 0 for staying in the same spot, right? So you see how there's a policy-dependent transition probabilities over here, right? So now, assume that you're starting with this policy, right? And I'm going to start off by, I'm going to try to compute the, so what was the, we had V pi equals R pi plus summation over all actions or over all states, P pi of states, because we can just sort of times, okay, V pi of S, sorry. V pi of S equals R pi of S, S prime, P prime of S prime given as gamma V pi of S prime. This was a recursion, correct? I'm taking the expectation over actions already. So now, this is my, and let me assume that gamma equals 1. So let me erase this guy for now. And here is my box, 2, 3, 4, 2, 3, 4. And this has shaded out, okay? And I'm going to initialize all of these guys with a value of 0. So this is my V0 pi of S, my initial estimate, okay? Now I'm going to scroll through all of the states and update it. So what is the, so you there, you're sleeping. So tell me what the updated values for these states are going to be. I said R equals -1 for everybody except these two guys, okay? What would the updated values for these states be? So over here, consider this one, right? At this point, what can happen? With a probability of 1/4, I can go this way. And when I go this way, my future has a value of 0, right? With a probability of 1/4, I go this way, the future has a value of 0. With a probability of 1/4, 0. And I have a factor, and again, so no, because regardless of where I go, my current estimate for the future value is 0, correct? But then I expend a -1 in the current state. Because you have this guy, right? You have the current reward plus the expectation, right? So this is going to be, no, -1, because all of the rest are 0, right? Right, and so all of them are going to be, my first iteration, everything's going to be -1, right? Because everything was initialized as 0, the expected future values remain 0 because every state has been initialized to have a value of 0. So my first guess is -1 for all of these guys. This is easy. Now this one, now my second iteration, what is my expected value for this state, for this guy?
So you take -1, you take, I guess, like the probability of going to the next state multiplied by the reward at that state. So, so -1 plus 1 times 1/4, plus -1 times 1/4, etc., etc.
So this is going to be -1 times 1/4 plus -1 times 1/4 plus half times -1, right? And there's plus 1, actually no, plus 1/4 times -1 plus 1/4 times 0, right? So that's going to, and then you have the current expense of -1. So that's going to be some 3/4 times plus -1, is that right? That's going to be -1.75. Right, what about this guy? Earlier this was -1, so it was, 1/4 times -1 plus 1/4 times -1 plus 1/4 times -1 plus 1/4 times -1, and then the expense of making that step. So this guy would have been -2, right? And I think all of the rest of them are going to be -2, except this is going to be -1.75, and all of them become -2. Which one? This is 1.75. Which one? Shouldn't this be minus 2? So these two are going to be 1.75. And everything else is going to be minus 2, right? So just see what happened. Now I want you to think back about the first thing we discussed when we spoke of chess games, right? When we spoke of chess games, you won a game, and what did you really learn about when you won the game? About the move that just preceded the victory, correct? So the moment you won the game, the first time you updated yourself, you learned about the moves that just preceded victory. This is very similar, correct? Now, iteration number 2, what are these values going to be? So what would this value be at the next iteration? This is going to be 1/4 times minus 2 plus 1/4 times minus 2 plus 1/4 times minus 1.75 plus 1/4 times 0, and then there's the extra minus 1 for taking the step, correct? That's going to be something like whatever, 5.75 divided by 4. What is that? Let's assume it's 1.5, right? So this is going to be the equivalent of minus 2.5 or 2.6 or something of that kind, correct? But now this was a minus 1.7, remember? So now when I take the average for this one, it's going to be, minus 2 times 1 over 4 times plus minus 2 times 1 over 4 plus minus 2 times 1 over 4 plus minus 1.7 times 1 over 4. And then there's a minus 1, correct? So that's not going to be quite minus 3. It's probably going to be like minus 2.9 or something of that kind. So you see what's happening. Every iteration, the value from the boxes is kind of seeping outwards, right? As you work your way out. Okay. And so I need the clicker. So here's exactly what happens, and so you can see that's pretty much what we worked out, correct? This is exactly what happens, as you can see. He's rounded down. This is cut and paste from the book. Now observe something interesting over here, right? The policy I'm using is a random policy, okay? But then as I iterated, if I just chose, I'm not modifying the policy, but hypothetically, if I were to use the current set of values to modify my policy, right? What is the policy I would choose? I'd choose the best, most rewarding future step, correct? I'm always going to go towards the guy which has the highest value. And in that case, you can see that at this point, for these guys, it doesn't matter which way you go, but for these guys, the most optimal thing is to go left, right? When you get, after 2 iterations, the policies are becoming a little more defined. And after 3 iterations, you get a policy that never changes again. Just based on, we are not actually using those policies in the iterations. We are still using our random policy for iteration. But based on the values that you computed, if you were to decide a policy, you find that it gives you a completely different policy than the one you began with, right? And this policy is actually better than the one you began with because it's likely to get you home much sooner, right? It should give you a hint that how can you actually compute the optimal policy. If I start with a policy and find the value, from the value I can update my policy and repeat the process, right? So which leads us to this business of, okay, given we've done the business of prediction, given a decision process, we can compute the policies, but then can I actually find the optimal policy, right? And for this, go back over here. This is basically what we saw, right? We found that even though I'm computing the functions, the value function using one policy, if I actually look at the values that I compute using that policy and use the simple greedy approach of choosing the most promising action from each state, that's going to give me a policy which is better, right? If you use this policy over here, instead of the random policy, the values would go down the values would improve much faster, right? And you'd get much better values. And so here, for example, it says at K10, the value associated to this guy is minus 6.1, which means that if you use a random policy, you're going to take 6.1 steps to get home, right? On average from this one, because each step costs you minus 1. So minus 6.1 is the equivalent of taking 6.1 steps. But then, if you chose the policy that actually derived from these same values, you would have gone home in just one step. So if you had used this policy instead of the random policy, the values assigned to each of the states is going to be much better, right? The two blocks adjacent to the black squares are going to have value minus 1 as opposed to minus 6.1. So this kind of gives us a hint of what we can actually do. Start with any policy, for example, a random policy, right? Use the prediction dynamic program to find the value function for the states using that policy. You can compute the action value functions from the value function, right? And then update your policy. And then use this new policy and go back and do this guy. But then here is the thing, right? So here's the overall process. Start with any policy, use the prediction dynamic program to compute the value functions, and use those values to directly. You don't even have to compute the action value. You can just use this formula over here to pick the best policy at each state. And now you have an updated policy. You can go back and redo the whole process, right? And keep doing this. This is called policy iteration, right? So in each iteration, you find a policy, and then you find its value, right? So now this will provably converge to the optimal policy. Why is that? Because it's very easy to show that if I compute the current values and then update my policy based on the current values, the new policy is going to have a better value than the current policy, right? If I use that value to compute my values and then update my policies, that policy is going to be better than what I had earlier. And now we also know that there is a unique optimum, that there's a unique optimal policy in a value, optimal value for every state, which means because it keeps increasing and there's a unique maximum, the value function has to keep increasing as you go through this iteration. And because the value function continues to increase, eventually it has to find the optimal value, and the corresponding policy is going to be an optimal policy. So this is guaranteed to converge. Okay. Now, so this is the general. Now I can, instead of using the specific approach that I showed you, there's something called a generalized policy iteration, where I can use any algorithm to find the value function, and given value functions, I can use any algorithm to update the policy. And this is also guaranteed to converge. So you don't necessarily need to use Bellman's equations. You could have used any other thing, and the whole thing still works. So the actual procedure to find an optimal policy is going to be something like this. Start with a value function, use any odd procedure to find a policy. You start, which is expected to improve the value. Use the value. Use any odd approach to compute the values for the policy. Yes.
So in one of the slides, just said your convergence when the policy no longer changes. Is it guaranteed, like if from one iteration to the next, if it doesn't really converge, or is it possible that like there's some large reward that's far away that would take some time to propagate?
If you're not changing anymore, the policy is frozen, so that's guaranteed to be the optimum.
Okay, so you just have to check from one iteration to the next.
That's it. That's it, right? It's going to find an optimal policy, but there's a unique optimal policy value, right? Optimal value, and it's going to find the optimal value. All optimal policies will have that same value. So it doesn't matter which of those policies you choose, you're winning, right? Or as close to winning as you can get in that particular game. Now, so here is another thing. All states will hit their optimal value together if you're doing this batch updates, which is beautiful, right? And so a policy has optimal value if any state in any state, if and only if for every state S prime reachable from S, the value for the state under that policy is the optimal value for the state, right? Kind of makes sense. You can't be at a suboptimal value for one state and be at optimal values for the next states, because then you're just going to change your current, the policy for the current state, and now you're going to be better, right? So this kind of anyway. Here, let's focus on this. What did we do in the procedure that I just showed to compute the values for states? I gave you a policy, and then we went through this little iteration repeatedly to find the optimal, find the values for all of the states in the system. And then once you found out the values for all of the states in the system, you went back and iterated again and found all of the values for all of the states. Then you iterated again and found the values for all of the states, and kept repeating this process till it converged. On the other hand, when we actually looked at our grid world problem, you found that you didn't have to compute, perform infinite computations, right? When this converged, the actual value for the state is minus 14. And you needed a hell of a lot of computations to get to this point. But the optimal policy was discovered after just 3 iterations, right? So given this, do you really need to find the actual values, let the dynamic programming converge before you update your policy? Clearly not. Seems to me that you can stop much short of that, right? So now let's, yeah.
So you have an ideal situation wherein you can find optimum, but what if you have a distribution where it's just a mirror image? So if you take the homes are in 2 corners, what if you put them in the other 2 corners?
That's a different game, right?
Never converges.
What do you mean?
So it keeps changing.
No, if you're going to change the game from iteration, if you're going to be changing the rules of the game from iteration to iteration, then of course that actually becomes more of an adversarial situation. We're not speaking of that. But given this guy, given a setup, given a specific MDP, right, you're guaranteed that there is a unique value for optimal value, and you're guaranteed that you're going to find it. But for any given policy, this iteration is also guaranteed to find the values, right? So if from iteration to iteration you keep flipping that, then your reward functions are changing from iteration to iteration, right?
My question is, if you have the home states, the other 2 corners as well.
It does. So if I have 4 home states, I'm going to get a different value, right? The values will be different, that's all. In that case, the optimal policy from here is to go right, that's it. Not to take 2 steps left. You'll find this out, right? That's all. Okay. So we didn't actually need to run this DP to convergence in the grid world, right? The optimal policy was found long before the function converged. So do we actually need the prediction DP to converge? Not really. So what we can do is to say, instead of letting the prediction DP run for infinite iterations and then changing the policy, I can let it run for just some L iterations. In the grid world example, L equals 3 gave you the optimal policy in one round, right? But instead, I could just run it for some L iterations, and then find the greedy policy, use the greedy policy, and go back and go through L iterations of the dynamic program, find the greedy policy, and keep repeating this process, right? And this will provably converge to the optimal policy, guaranteed. But then what is the value of L? It turns out you don't even need to perform L iterations. So here is the crazy bit. In the dynamic programming step, I can just perform one step of the dynamic program and then update my policy. And then use the new policy for the next estimate of my value functions and then update my policy. And then use that new policy to update my value functions and then update my policy. And this is also guaranteed to converge and will give you the optimal policy eventually, right? So it's kind of beautiful. So literally, this is just it, right? I can say policy k plus 1 is going to be the greedy over the value functions in the kth iteration, and vk plus 1 is simply going to be a one-step update using policy k plus 1 over vk, right? So this is it. This little iteration is going to be obviously much faster than the entire policy iteration, right? Now there's a Yes.
That greedy approach is the same as exploitation instead of exploration, or where you're only like you're updating after that first.
The exploration was it's kind of related, but not exactly, right? So, no, but because exploration versus exploitation, here the system is known. Exploration versus exploitation is when you're trying to explore the system to find other things, right? So, well, I said you start with any policy. Clearly, starting with a policy doesn't tell you anything. What you're really going to need to start with is to set an initial value for all of the states, right? But then if I set an initial value for all of the states, then I can initialize my policy, but why bother? Actually, I can actually start off with finding the optimal policy, then doing a one-step computation of the value and iterating this process. And this little algorithm is going to be, actually going to give you your optimal policy. But then I don't need to explicitly find my policy and then find the value. Turns out I can just merge the two into one step, right? And so this is simply, all I did was move the max inside. So if you look at what's happening over here, for each state, I picked the action that had the highest current value, right? Action value. And then use that policy to compute this guy. But then what I had done was to pick the action for which this term was highest and set the probability of that one alone to 1 and the rest of them to 0, right? So this is strictly the equivalent of saying, find me the max over all of these guys, because I'm only choosing one action. And that specific action is the one that maximizes this term. Currently, there's no randomization of our actions. So once I begin deciding that I'm going to add some noise to the actions, that goes into the exploration versus exploitation. Right? Here, this is strictly greedy, right? Okay, so, but you see what is happening over here. So this is a very simple little iteration. There's no explicit policy estimation. All you're doing is you're directly learning the value. At each iteration, you're learning the value for the next iteration. This is called not surprisingly, the value iteration, right? Earlier, what you were doing is you were finding the value, then you were updating your policy. Then you were finding the value, then you were updating your policy. Then you were finding the value, then you were updating your policy. It's a policy iteration. At each step, you're actually trying to find a policy. Here, you just have this little iteration where you have a current set of values. And then you're going to say, if I use the optimal policies under the current set of values, what would the values now be? How must I update the values? And this is the formula you get, right? And then you say, okay, now I have a new set of values. If I use the optimal values for the policy for this set of values, how would the values change? And then you compute a new set of values, and so on. So this is the value iteration. Now, the arithmetic, as you can see, is all really very simple. It's surprisingly simple for a topic that sounds very profound and complicated, but makes sense. So this is your value iteration, right? At each point, now observe that you're going to, the kth iteration for your estimate for the optimal value for any state is going to be the best over all actions of the action dependent reward plus the discounted expectation over all actions, right, of the values computed for optimal values computed for all states in the k-1th iteration. So this is exactly just your value function update. Remember, now this is absolutely no different from the exact same code or algorithm that you had when you were trying to compute the value functions using this little arithmetic trick that we saw, right? Except that instead of just doing this guy, instead of taking an average, you're just taking the max. One little flip, and the whole thing is guaranteed to give you the optimal policy. Very pretty. Right. So here's the value iteration example for the same thing. If you start off by setting everything to 0, right? The value iteration for the first guy, it's obviously everything's, as we saw in the first step, everything is -1. But now, you're always going to pick the best possible future. You're not averaging over all of the neighbors. You're saying the cost of going to the neighbor plus the value of my best neighbor, right? So if I do this over here, from here, the cost of going to any neighbor is -1. The value of the best neighbor is 0, right? So all of them are going to become just -1, no big deal. But then at this point, for this guy, the cost of going the next step is -1, but the value of the best neighbor is 0. So the value stays -1, right? For this guy over here, the cost of one step is -1, the value of the best neighbor is also -1, so it becomes -2. And so you can see the values have changed, right? But the next iteration, it actually goes to -1, -2, -3. It makes sense, right? And you can see that in 7 iterations, you actually find the optimal. In this grid world problem, there's only one corner. In 7 iterations, you just found the optimal values and the optimal policy as a consequence. Right? Very easy. So, questions? I managed to get through to 197. Can you believe that? So practical issues. The updates can be in batch mode, meaning I can explicitly compute the optimal value for all of the states, the k-1th iterate of the optimal value for all of the states simultaneously, or do this sequentially through the states. You're going to find no big difference, and it will still work. So I'll stop here a few minutes early. Quick recap. What we did was we learned about prediction, estimating the value function given a Markov decision process and a policy, right? We learned about policy iterations, which said you find a value, start with a policy, find a value, update your policy to be optimal under the current value, then find a new value and keep repeating the process, right? And we learned about value iteration. You directly estimate the optimal value functions. So we worked with value functions. You can alternately work with action value functions. Now, why would you not want to work with action value functions? In value functions, for n states, you just had to update n terms. If you're working with action value functions, for n states and m actions, you're going to be updating n times m terms. So this is much more expensive, right? So why do I even bother talking about this when it's obviously a stupid thing to be doing? Because in the real world, this is what you're going to end up doing. In the real world, where you have a continuum of states and a continuum of actions, or a very large number of states and very large number of actions, you're never really going to be computing action values for all of the states. Imagine chess, or imagine Go, 10 raised to 160 states. You're not obviously going to be iterating over all of the values and then finding the action value pairs. You're just much better off directly working with the Q function, which is the action value function. And there's a reason I'm calling it a Q function, which was maybe Ryan can, everything that you're doing Q learning, are you right? Yeah. You're going to find out all about why it's Q when Ryan does his recitation. Because we are going to learn when you're not given the Markov decision process, you still want to learn the Q function so that you can predict the optimal policy. And that's the Q learning, right? And so, yes. We worked with planning. Somebody gave us the MDP, right? Next, nobody gives us the MDP. That's reinforcement learning. We'll look at that the week after next. Questions? Yes.
Simple question about the simple equation. I think the result should still be b divided by a instead of
B divided, you are correct. So I'm sorry. I'm just it's 1 minus 1 minus a. Yeah, you're right. That's what we wanted. So I make a mistake and nobody points it out for like an hour. Yes.
in policy and value iterations, isn't there a direct correlation between the number of states and the distribution of
The rewards, whether there's a correlation between the number of states and the distribution of rewards is a feature of the game or the environment, right? So they may be or they may not be. In the case of chess, you have 10 raised to 120 states. You have only one reward. You win or lose, right? So that's something that's not in your control. That's not for the agent to decide. That's the situation. That's the game. That's the environment. It's the world.
In a situation where there's no reward,
Why would you play?
well, maybe like chess or Go, it's easy, like either win or you don't, through the beginning stages, but like self-driving, I guess you could say that I would reward. Yeah, or like, well, how do you determine reward?
So here is the whole point, right? There is no, so the value is a substitute for the reward. Think about this, okay? So if you go back to this situation, this example, there was only one real reward. All of them had negative rewards. I could have made all of them 0 and made that one guy 1, and it would have been effectively the same thing, correct? Or I could have, but anyway, you basically win if you get to the corner. But what happens is you're sort of smearing the final reward over everything through the value, or like in the case of the spider, right? And so when I do that over here, I know that this guy gets me one step closer to winning than maybe going this way, right? So the value function ends up being a proxy for the reward. It's the expected return over all time, and even if the final reward is only going to be given at the end, and if you're assigning yourself a cost for spending time, right, which you always do, then you're still going to know which is better and which is not. So although it's not an immediate reward, there's an expected reward, and that is a justification by itself, right? Yeah. All right, folks, thank you. Next, again, reminder, Graham is going to be teaching on Monday. I will see you the Monday after.